No, you're fine.
Oh, no.
That's actually
Okay, lecture 13. Old handouts are down on the front. If you need them, we got our skeleton down there if you want to take pictures after class. So first exam is this Friday. Any questions or concerns? Review session tomorrow. Here's a couple other slides we'll use as review. They are not in your handout, but we talked about the three different types of muscle tissue: skeletal, cardiac, and smooth muscle. We talked them being striated over here on the left or right side, and voluntary. So knowing the difference between those two, providing you with a little extra information that I will not be testing you on. So what do those functions do? We're hopefully at some point going to figure out all the skeletal muscles and getting that horse moving through time and space. So another drawing of those. We showed last time in our myofibril that the Z lines are organized in such a way that they create striations. Same thing over here with our involuntary or smooth muscle. We don't have that organization, so we don't get that definitive striation as we move through. The contractile units are not lined up in such a way that they're going to form the stripes we see over here. So that arrangement, we talked about the striated muscle, the cardiac or the skeletal, lining up, organizing. We have a different arrangement here that does not form those nice neat lines. We have things sliding over each other just like we do, or we haven't talked about that yet, but we will today. But we're not going to get the unison from a visual standpoint. So again, looking at different pictures, make sure these get up there. There, so get out your letters. Let's see what we learned from last time. So X marks the spot. What is X? A, Z line or disc, the A band, the I band, or the M line? So we're looking down the center here of our sarcomere. That is D, the M line. What is that? As part of our sarcomere. Same choices. So we're looking from one end of the thick filament to the other. That is our A band, our B answer. So that means this, starting here at the end, going over to the next end of a thick filament is called what? Here to the next thick filament is the I band. Last one is the what? Find or outside our ends, that's the Z. So if we go M in the middle, M is the middle of the alphabet, Z is at the end. So the Z disc or Z line, depending on what your frame of reference is. Which protein are we dealing with here? The thick filament is made up of what? Actin helix, myosin complex, troponin, or tropomyosin. So we're looking at the thick filaments here. They are the myosin complex. What are these? Also called the thin filaments. A is probably the best choice up there, but I have to accept C or D, and we'll see why in a minute. But the actin helixes are the most visible presence there. So everybody got their parts figured out. So let's do a little bit more about the structure. So we start with this diagram here, and we're going to zoom in on this bottom part here. So as we have the individual protein molecules, their final tertiary structure, we combine these together to get the myosin filament. That's a quaternary structure. We do the same thing with the actin little globules. We form a double helix here. That's our quaternary structure there. So these are our thin filaments. These are our thick filaments. What we also have to do, we've got our tertiary structure. We're building our quaternary structure. We need tropomyosin represented by the long lines and troponin as well to finish up the helix that's going to allow for movement. So you can see that these lines are now spiraling around up and down, and then we've got the troponin sitting on the top of various spots. So you've got 3 different proteins there. It's probably more than that, but we'll talk about 3 in this class that are going to provide the binding sites that actuate movement. Everybody see how all that comes together? So before we get into movement, I'd like you to take out a piece of paper. Does everybody have a piece of paper? Half sheet's all I need. I want to take your pulse, not to be confused with I want to suck your blood, right? I want to take your pulse. But he got something to write on and something to write with. Everybody know how to find their pulse. You know, on your wrist with your fingertips, or I just usually go up here, my finger, use the carotid. Everybody ready? No, okay. So while you're waiting, find your pulse. Don't push too hard. We slow the blood flow to the brain, which is not a good thing. Everybody ready? I'm going to count off for 15 seconds. I'll give you a start and an end. You tell me what number of beats you have in that 15-second block. Everybody ready? 5, 4, 3, 2, 1, start. End. Everybody got a number. So your pulse is usually measured in beats per minute, so I need you to multiply that number by 4. You can't do the math in your head, just put whatever number times 4, I'll do the math for you. Everybody got something written on paper? Pass them to the aisles. ID, Morrisville ID number.
Actually, you're making
Yeah.
That takes down.
So the attendance sheets in the back, it'll work its way down. Doesn't matter. Handle you. Doesn't matter. Error, you'll watch out when I show you what we're doing with this. Anybody else coming around the other side? One down there, getting over on the side.
You better be checking what plans for held out. I was like. Give them to. You know, they were
Anybody else? Got one more down front. Thank you. Okay, let's get to muscle contraction. So last time we talked about the nerve impulse coming from the central nervous system, either up in the brain telling us to do something, or a reflex that we'll find in the spinal cord. That nerve impulse, that electrical current, ends at the sarcolemma at the myoneural junction. We talked about one nerve to one muscle because yes, they're set at birth because we can't be rewiring every time we do stuff. We need the nervous system and the muscle system to work together. And we talked about acetylcholine is the transmitter. So this acetylcholine is going to go across to the sarcolemma and effectuate the removal of calcium from the T tubules. It's going to be released into the sarcoplasm. It's going to diffuse all the way through the cell. We can think of the T tubules constantly trying to get the calcium back. Every time impulse comes down, it gets hit in the back of the head and drops all its calcium. You drop that calcium, that's going to allow us to start contraction. So last time we talked about what happens if you can't stop that contraction, right? Tetanus is involved in that. So positive feedback system, the more pulses you get, the more hits on the back of the head and the T tubules. We continue to spill calcium into the sarcoplasma. We're going to get more contraction. That will continue till either the nerve impulses stop or this enzyme gets rid of the acetylcholine, breaks it in half, sends it back to the nerve. If I break it in half, it can no longer do that impulse on the other side of the myoneural junction, the sarcolemma side. Another enzyme is going to be located on the myosin heads, and we'll get to showing exactly where that is. This is called ATPase. Does everybody know the nomenclature for enzymes? ASE tells you what it breaks apart. So an enzyme that is going to break acetylcholine, choline esterase, breaks it there. This is an enzyme that's going to break ATP apart, release that energy so we have the power to move forward. So what events must happen for a muscle to relax? We've alluded to these before. We have to stop the impulse. We have to gather up the acetylcholine, and we need to get the calcium back in the T tubules or sarcolemma, sarcoplasmic reticulum. So we need to end the impulses coming in, the electrical signal. We need to put the calcium back in those T tubules. Again, they're trying always to gather that calcium up. With that removal of calcium, with the removal of stimulation with the acetylcholine, the muscle relaxes and can potentially slide back to where it started. It depends on the force. If we have weight on it, this muscle's relaxing. But if I'm just holding this arm here, it's not going to go back to its original length. It'll still relax, but it's not going back there. So it's kind of a passive approach. Contraction's an active approach. The potential to slide back to where you started, our pre-contracted state, is related to what position and what pressures we have. So let's move into the cell. What happens once we get into the cell? We've got the macro view of the nervous system communicating with an individual muscle fiber. So in order for a contraction to happen, we need a cross-linking between our thick fibers and our thin fibers, between our myosin complex and our actin helix. We can think about it as the itsy-bitsy spider going up the water spout. The legs are the myosin complex reaching out on all sides of the spout, which is a pretty big spout, right? And then our actin contact points are the spout going around. So we talked about that hexagon formation of our thin filaments around the myosin complex. We need to form that cross bridge, and we need to add energy to the system. ATPase is going to increase and release energy into the system. So this is how it all gets done. So what are the steps that are involved with that? Once the calcium is in there, it does a series of steps that allow for that connection to happen. With that attachment, we can move and contract our muscle. So everything is set up for muscle contraction. So what are the players in muscle contraction? We've alluded to most of these already. So the myosin complex with its enzyme on there, that's attached to the myosin, so it releases the energy right where it needs it. You got the actin helix, tropomyosin, and troponin all working together to form the thin filaments. We've got calcium coming in, we've got magnesium as the catalyst, and we've got our energy source coming from the mitochondria, ATP, which is going to break apart into adenosine diphosphate, one inorganic phosphate, and the energy to move. So at the molecular level, we start out with a myosin complex flex. We have, if you saw on the diagram there, you have the arms and then you have a head on it. It's flexed and ready to go. The ATP is attached. That's there to allow movement. Calcium enters and binds with troponin, which is on our thin filament. Once it's attached, it's going to act as a crowbar. And it's going to roll the troponin, the tropomyosin, over to the side. We're going to pry on that. As troponin rolls over, it's going to pull tropomyosin with it, and that long string of black line there is going to expose binding sites. Normally, those binding sites are covered over, but when calcium comes in, it's going to roll everything over. Now we've got binding sites. We have a place for the myosin head to attach. Binding sites are open. We are now going to get that cross-linking between the myosin complex and the actin helix. So, myosin complex extends to a binding site. We go from a flex state to an extended state. It's going to reach forward to get a binding site. You can think about it, your hands climbing a ladder. Pretty easy to reach up to the next rung. The energy comes when I pull things forward. So it's going to reach up to that binding site, bind. Magnesium is going to come in, act as a catalyst. It's going to activate that ATPase, which is going to release the energy from ATP. And what do you guess that's going to allow us to do? Flex. It's going to allow us to pull up the ladder. So we release that energy. The myosin head flexes. Calcium is released. Fresh ATP comes in, and we repeat the process all over again. Everybody got it down cold? At this point, the answer is no, right? You don't quite have it down yet. A lot of new words, a lot of abstract concepts happening. We're trying to make this real as we move forward. So in simple words, as opposed to all these big words, what happened? Myosin's kind of sitting there. ATP is ready to go. Calcium comes in, pries open the binding sites. Myosin says, hey, I can reach that. Then we add energy to the system and the system flexes. Pulls that whole thick filament closer to the Z line as it flexes. So setup, prying, we're exposing, we're reaching out, and then energy allows us to flex or move the filament forward relative to actin. So there's lots of videos online. This is the best one. I like the one I had before, but this is the best one I could find. See if we can make this work.
All skeletal movements. Skeletal muscles are composed of muscle fibers, which in turn are made of repetitive functional units called sarcomeres. Each sarcomere contains many parallel overlapping thin, actin, and thick myosin filaments. The muscle contracts when these filaments slide past each other, resulting in a shortening of the sarcomere and thus the muscle. This is known as the sliding filament theory. Cross-bridge cycling forms the molecular basis for this sliding movement. Muscle contraction is initiated when muscle fibers are stimulated by a nerve impulse and calcium ions are released. The troponin units on the actin myofilaments are bound by calcium ions. The binding displaces tropomyosin along the myofilaments, which in turn exposes the myosin binding sites. At this stage, the head of each myosin unit is bound to an ADP and a phosphate molecule remaining from the previous muscular contraction. The myosin heads release these phosphates and bind to the actin myofilaments via the newly exposed myosin binding sites. The two myofilaments glide past one another, propelled by a head-first movement of the myosin units, powered by the chemical energy stored in their heads. As the units move, they release the ADP molecules bound to their heads. The gliding motion is halted when ATP molecules bind to the myosin heads, thus severing the bonds between myosin and actin. The ATP molecules are now decomposed into ADP and phosphate, with the energy released by this reaction stored in the myosin heads, ready to be used in the next cycle of movement. The myosin heads resume their starting positions along the actin myofilament and can now begin a new sequence of actin binding. The presence of further calcium ions will trigger a new cycle.
The skin covers the body and protects it from the external environment. It also prevents water loss, provides
So everybody see our sequence now. Reaching out with that myosin head, a thick filament, and we're trying to climb up. Every myosin or thick filament, myosin complex, has lots of little hands on it. Clubs reaching out. They're going to climb up that actin. You've got 6 sets of binding sites all around that, and they're going to spider web all the way up. Is everybody following that? So as long as calcium is present, what is calcium doing? Holding open those binding sites, prying the troponin and tropomyosin out of the way. If the T-tubules say, hey, I got all to have that calcium back, and they get it all back, what happened? Reverse crowbar, right? Everything rolls back, covers the binding sites. What happened? Myosin can't grip anymore. Everything slides back to where it started. Calcium comes in, opens the binding sites. Myosin ratchets up, ratchets these thin filaments together, ratchets toward the end or the Z lines, and contracts that sarcomere. If there's enough calcium there, we'll contract the whole muscle. Take the calcium away, binding sites get closed. And everything, I can't grip, I got no hands on the ladder anymore. I'm sliding down. Everything can slide back to where it started. That's starting to make sense. So we're looking at the contraction pictures we used before. You got the thick filament with the myosin heads on it. You've got the thin filaments, the actin helixes with the binding sites. So you're going to move through up and down. So calcium comes in, it climbs up, draws everything together. So you got both ends working in opposition, drawing those actin helixes together. We take away that calcium, everything relaxes, and we slide back to where we were. So depending on where we are, whether the calcium is in the T-tubules or not, so another diagram of the same thing. The calcium is present, the thick filaments climb up the actin helix. When calcium goes away, we lose that cross linkage, and with that loss of cross linkage, we start back to where we were. So again, that finger example, nothing is changing in length, but we're moving our wrists closer together. This all starting to make sense. So let's make sure we know how to do this. I'd like about 17 students down front, give or take. So whoever's down here doesn't have to talk. People in the seats, I will ask you to contract the muscle. I will ask you to speak. So just come down here. We'll get you organized in a minute. Like a few more if we get them down here. Five or so more if we could. Okay, our volunteers down here, let's get them organized. So we're going to make part of a sarcomere. So who wants to be calcium? You're outside. So going through that door, where's she going? Well, I'll let you hold the door open so you can hear what's going on. What is she? She's calcium. Where is she now? Outside of the classroom, but specifically where? Where in the muscle cell is she? Where is she? She's being stored where? Not in the bone at this point.
Yeah.
Maybe at one point she was. They're in the T tubule. So we are waiting calcium release. When does calcium get released? Nerve impulse comes. Pops it on the back of the head. I drop all my calcium. It is. Okay, so we've got that part figured out. Okay, I need, what do we got here? We got I need 4 of you to be myosin, 8 of you to be actin. Actin stays on the table line, myosin steps out. Okay, so I got 3 of them. I know you guys would be so excited, right? Here's the big box.
Oh.
Okay, so actin, I want you evenly spaced across those tables, facing that way. So what does actin do? What does actin do? Give me an answer. Actin provides what? Binding sites. How do we expose those binding sites? Calcium comes in. Nerve impulse, calcium comes in. Calcium, come on in. Okay, so actin. We're going to represent our open binding sites by doing this. So either we're going to be closed or we're going to be open. Everybody with me so far? Actin, you know what you're doing? Calcium is present, so what are you doing? Open, put your hands out, we need binding sites. You're calcium, you don't need binding sites. So everybody's putting there, we now have binding sites. Myosin, space out and turn around. No, we're not. Okay, so you're going to take your myosin, hold it out. Calcium is present. What can you now do? A little forward. You can now cross-link and bind. What happens if calcium goes away? We lose our impulses. Calcium, go away. What happens?
Bye, calcium.
By calcium, what happens? Hands go behind your back. We have no connection anymore. Without that connection, we cannot move parallel to each other. Calcium back in. Actin, calcium is here. What happened? Okay, so we have a cross linkage. What happens next? Myosin takes a reach out to the next spot. So don't move your body, just move your thing there. Going the wrong way here. Everybody go to your left. One to your left. Right? Then what happens? The energy from ATP does what? We ratchet forward. It flexes. So we're going to flex our myosin. So what happens? Myosin moves to the left and lines up again, right? As long as calcium is present, then what? It moves again. We reach to the next spot. Energy is released. We flex again. Okay, nerve impulse stops. Calcium is scavenged up by the T tubules. Calcium goes away. What happens? Now what happens? Disconnected. Everything slides back. So slide back to where you started. Is this at all helping? A little bit. Starting to visualize it. Do we want to record this to have it up somewhere?
Yes.
Okay. You gotta first prove to me that you, as a class, can lead this through. So, what is our first step? I get recording with mine. Calcium comes in. What does that do? Provides our binding sites. Opens things up. Provides our binding sites. Then what happens? ATP attaches, releases its energy into that head. Then what does that head do? Reaches to the next spot and contracts, right? So we're reaching to the next spot and contract. Reaching to the next spot and contract. And we keep doing that till what? Calcium goes away or ATP goes away. We need both. So calcium goes away. There we go.
We're broken up. I'm back, guys.
Anybody down here have any objections to being put up on YouTube?
Stop it. I'm be famous, bro?
I've had upwards of 10 views, so you know.
Should be tagged me. They need to clown.
Yeah, what percentage of the money do we get?
Yeah.
I don't get any money from anything.
If we go big, I'll do 95.
If-
like higher.
If there is somehow a large windfall of money, and we'll split it proportionally with these, but with the entire class. They are walking us through. This is a class effort. They are walking us through. Okay, so here we go. Is everybody ready to talk us through this? Here we go. What happens first? Calcium comes in. What does that allow? Opens a binding site. We get cross linkage. ATP comes in. What does it do? Releases. We need a stretch, and then we release the energy to do what? Move, to crank, to step, to move forward. More ATP comes in. Calcium is still here. Cross-linking, moving through. We flex again. One more. And we flex one last time. Calcium goes away. And then what? Put your hands away, the binding site. Everything slides back to the beginning. Is that everything you hoped it would be? Thank you for helping out down front here. So now if we want to put it in simple words, it's probably a lot easier than it was a few minutes ago, right? You've seen the progression. Again, that's a theory. That's the way we think it works. So you're looking at things that are happening very, very quickly. That diffusion of that calcium into the cell has to be very, very rapid. The transport of ATP to the from the mitochondria to the muscle cell, or from the mitochondria in the muscle cell, has to be rapid as well, if we're going to keep that train running. So you're going to flex, you're going to relax, flex, we're going to relax. Next time we'll talk about pairs. So do we have, hold on, we're not done yet. Got 4 minutes. Do you realize if I let you go 5 minutes early, I'm giving you 10% of your education? I'm here to educate. I want to get you $100 worth every lecture. So a couple other diagrams that you don't have in your handout, but might be when I post a little helpful as to what things are doing for the next task. So we have that myofibril coming out of the muscle fiber. We see the kind of histological view, and then we have the cartoon view. Remember that those thin filaments surround the thick filament, and that thick filament is reaching on all 6 of those things going up. Again, we're showing that calcium release. That calcium release is going to lead to that contraction. If you really want to get technical, and this is beyond what I will test in this class, we have an action potential coming down the nerve, a spike in electricity that has to be transferred over to the sarcolemma. So that action potential is going to release that calcium and allow that contraction to occur. So another picture of the T-tubules. We're releasing that calcium. It's got to be moved out into the myofibrils. That calcium has to flow in. The ATP from the mitochondria has to flow into those cylinders. So in each myosin head, we have a calcium and we have ATP. That cross linkage needs to occur. So I tend to think, I don't know if this is perfectly right, but it seems to me that the T-tubules are always scavenging calcium back. That's their job. And as I said before, the action potential, I drop everything. I got to get it back as quickly as I can. To allow that relaxation, to allow the muscle to cycle, that T-tubule has to be in a constant state of trying to get that calcium back into storage. It's being obstreperous and unruly. So flowing in, we see that up top there, that line is tropomyosin covering the binding sites. Calcium comes in, moves that protein over to the side, and in the middle up there, we have the binding sites open. Now myosin can link to that. We flex and the contraction begins. So that's all I have time for. We'll see you on Wednesday. Yes. Yeah, we have the Dairy Club review session. If you can hold off till 6, we got some things that we have to cover at 5 with some of the dairy students. You come at 6, or you can come at 3 tomorrow, whatever you want. So, okay. So yes, tonight you're more than available. If that doesn't work, let me know. I'd probably be around Wednesday afternoon as well. Okay? Okay. Okay. Stop by. Thank you.